Today, I'm here to talk about something very simple, water, something that we cannot live without, a critical resource that has inspired and motivated all my research. I'm one of those Chinese people who ask for hot water at a restaurant because I grew up drinking boiled water. And that's how we used to make drinking water safe back in China. When I first came to the US, one of the first things I learned was that one could actually drink water directly from the tap. I was so impressed by the convenience it brought to my life and the trust that the public had in our drinking water supplies, so much so that I actually changed my thesis topic from studying aerosol transport to advanced water treatment technologies. And so when I was asked, was our tap water safe, and should we install one of these water purification systems in my house, my answer had always been that read your city's water quality reports. Our tap water is safe. However, with increasing knowledge on the formation of disinfection byproducts and increasing reports on lead and copper problems in our drinking water, and experiences with boiling water notices, my confidence started to shatter. Over the years, we've learned about the different water quality-related crises. You may know about the lead crisis in Flint, Michigan. What you may not know is that between 9 and 45 million Americans get drinking water from sources that are in violation of the Safe Drinking Water Act. And so today, I no longer try to dissuade friends from installing home water purification systems. But I also understand that these home water purification systems are not our solution to the problem because not every single family can afford or knows how to properly use a home water purification system. Water quality is not the only problem we have related to our public water supply. Increasingly, we hear and experience water supply disruption due to infrastructure failure. Way too often, you see one of these broken water pipes with huge volume of water gushing out and running down the street. This kind of water main breaks is happening every 2 minutes in the United States. And from those broken pipes and leaks, we lose 6 billion gallons of well-treated drinking water every day, and that's billion with a B. And that is 15% of our total public water supply. And so all your tax dollars went under the drain, literally. And closer to home, last year when we experienced the freeze, 1,180 public water systems experienced service disrupting, impacting 50 million residents in the state of Texas. So those are not what we expect from our public water supply system in the 21st century. What went wrong with our public water supply? Water treatment was one of the greatest engineering achievements in the 20th century, a great factor in the declining urban death rate and one that greatly contributed to the doubling of life expectancy of Americans. A traditional municipal water system usually takes water from a river, a lake, or a reservoir and treats it in a large centralized water treatment system to the drinking water quality, and then deliver this water to each individual end user through a massive distribution system. Now, transporting a huge volume of water through a massive distribution network is very energy intensive, usually accounting for more than 75% of the total energy consumption for water supply. Do you know that there are more than 7,000 miles of pipeline in the city of Houston's drinking water distribution network? And that's a huge amount of maintenance cost as well. At these individual use points, we use potable water for all sorts of purposes, flushing toilets, washing your cars, and watering the lawn, which does not require the same quality that is needed for water for drinking. After use, Our massive sewage system collects the wastewater, sends to gigantic centralized wastewater treatment plants for treatment, and we remove particulates, remove most of the organic matter, and disinfect the water, and then discharge this water back to our surface water bodies that are usually used as surface water supplies for cities downstream. And what I should mention is that our Victorian era wastewater treatment technologies that are still used in most of the wastewater treatment plants today are not capable of removing many contaminants of concern, including nitrogen and phosphorus, which are valuable fertilizers for agriculture but can cause very harmful algal bloom in our natural aquatic systems, and pharmaceutically active compounds and personal care products that are very harmful to both human and ecosystem health. We need to redesign our urban water supply systems. We need a water system that's more energy efficient, that's more water efficient, more resilient, can recover valuable resources, and most importantly, do not contaminate our natural environments. Instead of relying on only centralized water and wastewater treatment plants, we can put in place smaller scale, distributed systems that collect wastewater, stormwater, and other locally available alternative water sources, treat them differentially to quality required for the various potable and non-potable applications, a concept that we call Fateful purpose treatment. And these distributed water supplies can supplement our centralized water supply, and therefore we don't have to transmit a huge volume of water through the system, and we can save energy associated with water transmission. At the same time, we will also cut down the waste we discharge into the natural environment. The concentrate from this treatment contains very high concentration of nitrogen, phosphorus, and organic carbon, which can be harvested in the form of nutrients and energy that can be used for local irrigation as fertilizers, as well as to supplement our electrical energy supply. And these distributed systems can also be interconnected and coordinated via a central control system. Now, the challenge for such an attractive approach is that there are currently no available quantitative models that can allow us to characterize and design such hybrid systems. Questions such as how many of these distributed systems we should install, and what scale or treatment capacity they should be designed for, and where they should be located cannot be answered yet. So my colleagues and I here at Rice University are trying to develop computationally efficient models that allow us to capture the essential physics of these very large systems without the complexity and the high computational cost of high resolution, purely physics-based model. And this, at the same time, is also a complex multi-objective optimization problem because different stakeholders may value each objective differently. And so we're also developing these multi-objective optimization tools so that our urban water managers can use them for decision-making to minimize energy consumption, minimize freshwater withdrawal, waste discharge, while maximizing the resilience and reliability of the water system, all at minimum cost based on their specific needs. I'm going to tell you a different story that happens in another part of the world that we don't usually see or hear about every day. A couple of years ago, some Rice colleagues and I went to Tanzania for a conference. Two little boys from the local Maasai tribe came to our car. My daughter gathered all the food in the car and gave it to the boys. But that doesn't seem to be what they were looking for. After a lot of signing and help from our tour guide, we eventually figured out that what they wanted were the empty plastic water bottles we had in the car. Maasai people live on their local tribe land. They do not have access to municipal water or the power system. And even though there are several lakes nearby and the groundwater aquifer is also relatively shallow, the water is saline and not suitable for human consumption. So they use these plastic water bottles to store whatever fresh water they can get hold of, and those are all they have as water sources. And so you'll be surprised to find out that globally, how many people have the same or similar problem as these Maasai boys. By the year of 2030, there will be 3.9 billion people living in areas that's impacted by severe water stress. And by 2050, our urban water demand will increase by 80%. That leaves us a gap of almost 7 billion cubic meter of fresh water short of our demand. And most of this water deficit will happen in areas that do not have reliable water and energy power infrastructure, which means that we cannot simply copy the method we use here to supply water in areas like these. So supplying water to this big population is an enormous challenge we have to face. What they need are treatment systems that can take any source water. It could be seawater or other saline water sources, could be wastewater and stormwater, and extract fresh water from it using various forms of energy that is locally available without having to rely on the power grid. So here at Rice, we work with 3 other partner universities as well as more than 25 industry members through our NSF-funded Engineering Research Center for Nanotechnology-Enabled Water Treatment, or NEWT in short. We have a bold vision, and that is to provide affordable and adequately treated water anywhere it is needed. Combining advanced materials and novel treatment processes design, we're trying to come up with compact, energy efficient, and very importantly, chemical-free treatment systems that can be deployed in these areas and take advantage of any source water, non-traditional or traditional, that is available locally, coupling them with the various forms of energy that we can harvest locally, being it solar photovoltaic, solar thermal, wind, waste heat, or even ocean waves, and so that we can operate these systems without relying on an energy system. Now, it's my hope that working with our current and future partners, we can bring solutions to these 3.9 billion people to give them safe water in the near future. Now, these same technologies can also be used in the distributed treatment and reuse facilities for our modern urban water supply systems that I discussed earlier. Because these systems can operate off the grid, so we can ensure water safety independent of the rest of the water infrastructure or the power infrastructure. So I hope that in the near future, I will be able to say in confidence again that our public water supply is not only safe, but also resilient and sustainable. And I invite you to join this effort in providing safe water to more people. Thank you very much.